the concentrically loaded double angle member under tension. So as you can see, can you see my screen? Just to make
Yeah.
sure you are seeing my screen.
Yes.
So the first problem is to determine the maximum design load in star for a tension member consisting of two unequal angle 75 by 50 by 8. UA means unequal angle as you can see here in figure 1. So the legs are not equal, B1 and B2. And the grade here is 250 steel connected through the parallel long legs. So they are connected through the parallel long legs. So it will be something like this by a single line, okay, of connection. And this is the dimension of the unequal angle where B1 is 75. So this 75 millimeter. B2 is 50 millimeter. The thickness is 7.2.8 millimeter. And the area is area of the cross section 917 millimeter square. So this problem illustrates the design limit state of member yield and section fracture of a tension member or member under tension. Okay, so this is the information from the example. Thickness is 7.8. If yield is 260. If ultimate of steel is 410. Okay. The first of all, we need to calculate area gross. Area gross of the cross section will be 2 because we have two angles times area of one angle. So the gross area is 1834 millimeter. Area net or the net area will be 18, the total area or A gross minus the holes. Okay, so the holes, I think there is maybe, yeah. So the hole here will be, we have two bolts times 18 is the hole diameter, phi hole, times 7.8, which is the thickness of the angle. So this area net. So this means that we have here one single line of holes, as it mentioned in the head column question head. So this hole is phi of the hole is 18 millimeter. So if we want to distract this from these two holes from the total area to get area net, so this area, one of them is 18 times the thickness of the web, which is 7.8. So we can get the area. Okay, KT, this factor is 1. So the member yield is NT equal to 1834 times 260. This is F yield. So NT equal to area net, area gross times F yield. So this is the yield of the tension member. This will give us NT equal to 476 kilonewton. For section fracture, we use the area net. So it will be NT equal to phi, which is the reduction factor of design, times KT times area net times F ultimate. So F ultimate is 410, area net this number, KT1, and phi is 0.85. So the value from section fracture is 541 kilonewton. So which one we take? So what is the maximum design force for this one, or the maximum capacity of this member? We will take the smaller or the larger? What do you think? Smaller?
Smaller.
Yeah, because smaller will be safe for both cases. So the final design force will be 0.9, which is phi s, or phi for tension member, times the smaller value, which is nt, smaller. So the final value or the final result of this example is 429.2 kilonewton. Okay. So this is the comment on the answer. The design controlled by member yield because it is the smaller. So that's why we picked this case. The hole diameter was assumed to be 2 millimeter greater than the bolt diameter. So here the bolt diameter was, you can add it here. So bolt is, don't know why it moved. This is because it is a table. So the bolt is 16 millimeter. So M16 was used here. Okay. So here,
Sorry, I just got a question with the FY and FU. Where were those values from?
the F yield and F ultimate. You mean this value, where does it come from?
Yes. Yeah.
Yeah, this depends on the grade of steel mentioned in the example. So the grade 250. So F yield is 260. F ultimate is 410. These values can be found on the tables. Oh, sorry, on like the, yeah.
The capacity tables.
Yeah.
Yeah.
Do you have your access to the tables?
Are they in module 1 or something like that? Or
No, I haven't added them, but maybe I will add them to module 4. But I mean, you can find them on the internet because
yeah.
You can find them online, but if we had like a place where like all of them were
yeah, they
basically
are
easy
all
access.
scanned, not because you have to pay for them, I think.
Yeah.
So I just try to share my screen with some of the table. But anyway, I will try to share it with you, even by email or something.
Yeah. No worries. Usually I
Can
just
you,
look. Yeah,
can
look
you
them up.
see? Can you see this now?
Yeah.
This table?
That's it.
Yeah. These are the tables. This is the name of it. Design capacity tables for structural steel. So if you are using like the standard steel sections like I-beam, C-section, T, and angle, so you can use this volume open 1 for open section. There is another volume for hollow sections, but depend on what is the sections you are using. Okay.
Thanks.
No worries. I will try to send this by email to you so you can access it. I tried to find a better quality scan, but I couldn't. But anyway, I think it is clear. Okay. Do you have any other question about this example, the first example?
Fine.
Okay, so this is the first example. And the second example is also about tension member. So, or maybe I will jump to, I will try to like solve one example for each case. So we can try more example, and then if we have time, I will return back to them. Okay, so I will jump now to example 4, which is shaking a universal column subject to compression. So this is an application of compression members. So we need to determine the maximum design load in star of a concentrically loaded, this is the section, 200 UC 52.2 compression member of grade 250 if the effective length about each axis is 3.5 meters. So LEX equal to LEY equal to 3.5 meter. As you remember from module 2, we have like buckling about buckling about X and buckling about Y. So we have two buckling lengths, but here it is given as both of them are equal. So this means that the buckling factor, because LE equal to K times L. So the buckling factor for both cases may be 1. This is the only case that both direction will be equal. Anyway, this is given directly that the buckling about X is equal to the buckling about Y equal to 3.5. And here is given the dimension. You can find this dimension in the tables. Okay. But if it is not given, this means if it is not given, you can find it in the capacity table. So I will try also to show you from the tables where to find the cross-section dimensions.
I think you can just look them up online. It's called One Steel.
Yeah, there is one, but the one steel doesn't have the plots for strength. Yeah, anyone you can find will be, they are same data, so it doesn't matter. Anyone you are happy to use is good. Okay, but I just want to show you the one because AISC is the official one from the related to the standard, the Australian standards. Okay, so we'll share the table now. Okay, can you see the table?
Yep.
There is no this one of the table, but there is not the case we are looking at. So all these tables are given the probabilities. So the first section of the tables is like section 3. This section is talking about the probabilities. So here is the section 3. So section 3 or part 3 of this tables are talking about the section probabilities. So you can find the section probabilities depend on what you are looking at. So if we go to the table, this table is for welded beams, but the section given in this example is UC, which is universal column. So I will go to universal column. So this is universal beam, and this is universal column. So here is the section we are looking at. UC, 200 UC, 52.2. So the depth is 206. The width is 204. And the thickness is 12.5. The flange the web thickness is 8. And so on. Okay. So I can, yeah, this is the one we want to do. So this is the dimension we looking at. Okay, can you use the table? Okay.
Yeah, thanks.
Okay, no worries. So these are the tables, and now we go back to the file, the example we are doing. So these are the dimension here, and this is the area, and Rx, Ry, which is the radius of gyrations we will need in the solution. So this problem illustrates the most common procedure used for checking a compression member. So what we need to know for here is T flange 12.5 and F yield depend on the grade is 250 MPa because this member is under compression, and we have like F yield for whip and F yield for flange. So for UC member, if yield is 250. Okay. So we have if yield of 250. But for your information, this grade is not existing now. So they replace it with 300 MBA. But anyways, it's just illustrative example. So whatever the grade given to you, or whatever the steel used in the design, or what is the steel available, so you can use the grade. Okay. So there is grade. The grades available now are 300 and 400, and for this for open section, and for like hollow section, right? There are two grades like 250, 350, 450. This for hollow section. So whatever the grade, the given grade is, you can find if yield and if ultimate. So here we will go through the procedure. The section properties, we need to know if the section is compact or cylinder. So we need to calculate lambda effective for flange and lambda effective for web. Okay, so here is lambda effective for flange. It will be, the formula for this one is B over T times I will just remove this one, rewrite it here. So we have B, this is B, flange, over this one is T flange, times root if yield over 250. So this is the formula for effective, lambda effective, which is the length or the width of the member, B flange, divided by the thickness, T flange, multiplied by F yield over 250. So here, if we look at the flange, if we go up, so this is the flange, but we only take half of the flange because this is the one we are looking at, because not the whole flange will buckle as a whole. So this half is the whole flange, which is 203.9 minus the web thickness divided by 2. So this is B flange. Over T flange is given 12.5 multiplied by root 250, which is F yield over 250. So here given, or the result will be 7.84, which is less than lambda effective yield for flange. E means effective, Y means yield, which from table in the standard equal to 16. Okay, so if it is less than yield, this means it is compact. For web, we will do same. So for web, if we look at the web, yeah, this is the height of the web we are looking at. So how much is this value? It will be the height of the web, the total height of the section, minus 2, because we have 2 flanges, divided over the thickness of the web, T web. So it will be D web over T web, again, times root 250 over 250. This will give us lambda E web equal to 22.65, which is less again than like this value here. So this value for flange from table, and this value for web from table. So we will get that this also web is flange. So this also web is compact. So the flange is compact and the web is compact. And from the standard KF for this section, the shape factor will be 1. So the final nominal member capacity, nominal section capacity, NS equal to KF times A, which is the section, the cross-section area, times 250, which is F yield, will give us NS equal to 1660 kilonewton. Okay, so this for the nominal section capacity. For the member section capacity, the member capacity, we can write here, we have a section capacity A and member capacity B. For the member capacity, we have to find lambda nx and lambda ny, and then select the bigger lambda n. So what is lambda nx and lambda ny? I think it's better to share the formulas from the module itself. So if we go to the compression member here, can you see the module now?
Yes. Yeah.
Yeah, so this is the equation of the design of axial compression. So we need to check the section capacity and the member capacity. Okay, so this is the section capacity. So we need to find KF. This is the equation first. NS equal to KF times AN F yield. So this KF depend on area effective over area gross. So for this case, we get that KF equal to 1 because it is a compact section. Okay, so then we have to go to, what we have done here. We get the plate element slenderness, lambda effective, using this formula here. We have used it for web and flange. We got lambda E flange and lambda E web. And using these two values, we get KF equal to 1, and then we get the nominal section capacity. This for the nominal section capacity. And here is the table from where we get lambda E yield for also web and for also flange, the values we have used. Then we will jump to the second part is the nominal member capacity, NC. So the nominal member capacity, NC, is using this formula, NC equal to alpha NS less than or equal NS. So now we need to find the value of lambda C. Okay. So to find lambda C, we need to use the equations here. So we have alpha c equal to zeta 1 minus this root, and zeta is this value, and here we have lambda n, which is called the modified member cylinderness. So first of all, we need to find lambda n, and this is the formula for lambda n, which is L effective over R times root KF times root F yield over 250. So if we go back to the other screen here, so lambda n x is 3,500 over 89 times root KF, which is 1, times root F yield over 250, which is same. So we get lambda nx equal to 39.3 and lambda ny equal to 67.8. So from this we got lambda n equal to 67.8. So if we go back to the other table, the other module file, sorry. So we have two options to find lambda c. The first one is after we got lambda n, we substitute to get alpha a and get finally lambda and then zeta and then lambda c. Sorry, alpha c. The other option is to use the chart. As you can see here, we have also chart. So you can get the chart from the chart, get also alpha b here. Okay, using this chart. Can you see the chart? So using this chart with alpha n we can find alpha b. So here alpha b will be 0. Okay, so here we got alpha b equal to 0. So return back to the other file. So here I will write down here from chart alpha b equal to 0. So alpha c will be 0.779 minus 0.779. And we get alpha phi c equal to 0.9 times 0.76, which is alpha c, times 1660, which is I think ns here. So this will be ns. So we have phi times alpha c times ns, and finally we get phi nc equal to 1138 kilonewton. Okay, do you have a question about this one? I think just we need to like write the equation here clearly. So I will try to rewrite this solution again with the equation besides or something to make it easier to understand. Okay, do you have any comment about this example or any query about this one?
So once you complete that, then you find phi nc. Do you need to compare that value to ns?
Sorry, can you repeat again, please?
So do you need to compare that value that you just found 1138 to 1660 to answer the question?
Yeah, you see here, I'll just share because this is the procedure for all like the elements. We have section capacity and the member capacity. So n star, I will write down another line here. So n star is equal to the smaller of ns and nc. So what is n star at the end here? So we have
Yep.
these two values, and we
Yep.
need to pick smaller, the smallest.
Thank you.
Yeah. So it will be 1138 kilonewton. Okay. This is what you mean, right?
Yeah, that's what I mean. Yep.
Yeah. So if we are checking like this one, this example means checking. So we are checking what is the maximum capacity could be carried by this element. So we have the element or the section or cross section ready for us. So it is given for us that the cross section is whatever given to us, which is 200 UC 52.2. So we need to find how much the maximum capacity of this section. So what you need to do is go to the, like using the equation, find phi ns, which is section capacity, and phi nc, which is member capacity, right? And n star will be the smallest of these two. Okay.
Thank you. Yep, that makes sense.
Okay, no worries. Thank you. So the other one is here is the design. The design is like another procedure different from checking, because here we need to sorry, this also checking. We need just to need to the title is mistake wrong here. This also checking. Why is it checking? Because it is given the section as well. So if the cross section given, so this is just a typo. So if the cross section is given, so this mean we are doing checking. So checking mean we need to find the maximum n star. So I will just jump on this one, and yeah, we need to go to another one. Okay, like this one. Here is a design example of a member under compression. So it is a design of member under compression. Here, as you can see, the cross section is required. So you are required to find a cross section. So we have a concentrically loaded compression member of grade 250. Is so restrained that its effective lenses are LEX. So it is given that the buckling about X is 8 meter, the buckling about Y is 4 meter. If the nominal dead load and life load are 300 kilonewton and 1000 kilonewton, design a suitable UC section. So you need to find a suitable UC section. So here we are looking about designing. So N star is 125 dead load or G and 1.5 life load or Q. So as you can notice here also, this was updated to be 1.2, but anyway, this is just a number here. So what is N star we have? So here it is given directly N star equal to, it is not unknown. So it is given us N star as 1875 kilonewton. So it is given the load. So what we will use, so here we have F yield is 250, KF is 1, alpha B is 0, alpha N is 100. So alpha C from the standard using this information will be 0.541. So A should be 1875 times 10 to the power 3, which is n star, divided by 0.9, which is phi, times alpha C, times KF, times F yield. So the area required for this section should be more than this value. Okay. And as you can see, do you remember what is this value is from the previous example?
You know that from the table?
Yeah, but if we go up to the previous example here, yeah, this will be from the table, but I mean, if you go back here, what is the member capacity was the formula for the member capacity? Phi NC. We'll go back here. Yeah, here. So this is phi NC. So phi NC equal to phi alpha C times NS, which is NS was area N or area gross times F yield. So what they have used here is to find the area required, we divide N star over the formula of N phi NC to get the required area. So the required area will be 15,404 millimeter squared. So we try a cross section, like from experience or whatever the section you use, because as you know, the design process is iterative process or trial and error, because you cannot know exactly the needed section from the first try. So we try the closest area to the section, to the required area. So here the required area was 15,000 something. So we go to the table and find that the closest area to this is 310 UC 1118. Okay. Do you get this one? So we go to table here, right down here. So we go to the UC table or the universal column tables using the required area here. Go to the tables of universal columns to select cross section. So we selected this one, 310 UC 118. This is the probabilities from tables Rx, Ry, which R is the radius of gyration about X and radius of gyration about Y. So what we will do is, again, we will find phi nx, lambda nx, lambda ny. Lambda nx will be L effective about X over Rx times root 250 over 250. So F yield is the first one and 250 is the formula itself. And this is Ry and this is Ley. So Ley over Ry times root 250 over 250. So we will find that lambda nx is 58.8, lambda ny is 51.6. So which one is critical? The critical from lambda is the largest, because this is like buckling factor. So this means when the factor is larger, so this means this is more critical in buckling. So we have lambda n is equal to the largest of these two, so it will be 58.8, and which is 100 we assumed in the first step. So lambda n will be 50.8.8 plus 100 over 2. This is average. So find lambda n equal to 79.4. So using the modified lambda n, we go to the chart to find the alpha b and get alpha c equal to 0.685. So the area of this cross section will be again n star over phi times alpha c times kf times f yield. This area is 12,165 millimeter, which is less than the required area 404. Okay, so what we have done is we got an area required here, area required. So what we do is go to the table to find the closest section to it and make the steps we have done in the check in the previous example. So we found that the area effective of this member is only 12,165, which is less than the required one. What does this mean?
We need a bigger member.
Yeah, this means that the member is not adequate. So here, because I don't know why this happened. Okay, sorry. So from this step here, we know that the section we have used 310 UC 1118 is unsafe, or sorry, is not adequate. Okay, don't know why they use smaller member. Okay, sorry, I just remove this one now. Okay, so we just make the second trial first. So this is first trial, and we will just leave it like that now, and then we will follow the example to see the second trial. So the second trial was a smaller member, which is 250 UC 89.5. So this is the dimension and properties from the tables. of the selected section, 250 UC 89.5. D and all the required properties. So here we will use this one to find lambda EF and KF and lambda NX, lambda NY, and lambda N. Okay, we didn't just consider the first trial here because we have assumed some parameters like as we mentioned here in this step. So as all this parameter was, sorry, this one was assumed. So we cannot just take the first trial. So we have like to try 2 trials and then judge. So I will leave the comment on the first trial now here. Okay. So for the second trial, for this member 250, we have to find the member capacity. So we will find lambda EF, which is again B flange over T flange root 250 over, or F field over 250. So here we got lambda EF equal to 7.09. Okay, which is less than the yield lambda. So this one is less than the yield lambda. This means this flange is compact and KF will be 1, lambda B equal to 1. And we will go to find lambda NX, lambda NY. So lambda NX LEX over RX will get 71.4, and LEY over RY we will get lambda NY 61.7. So this will be lambda N. So lambda N is 71.4. Okay. So lambda C will be this formula again from the standard. So we find alpha C is equal to 0.739. So phi NC, the member capacity, will be phi times alpha C times KF times A member times F yield, which we find that this value is 18.9. 1894 kilonewton, which is more than 90, more than the N star given in the first of the problem, in the start of the problem, which is 1875. So finally you find phi NC equal to 1894 kilonewton, which is more than N star 1875 kilonewton. This will give us that we can use 250 UC 89.5. Okay, so if we use the first trial as well, it will be adequate, but this trial is just to make the selection very close to N star. So just to be more economic, we got the smaller section. Okay. So now N star is this value and the grade and LEX, LEY. We got to try this one, which phi NC equal to 190. So this part is using tables. So up to here, we have find the cross section. Adequate cross section is 250, UC 89.5. Okay, if we continue from here and do same values, same procedure here, we find in phi NC, we will get also that phi NC is a value, let's say 2000 or something, which is greater than N star, and this section will be also adequate. But because the area was not close to the required area, so that's why he tried a smaller section. Okay. And this is for this example. Do you have any query about this example? Do you have any comment about this example? No?
Not at the moment.
Okay, thank you. So I will, can we continue for maybe 5 minutes here to finish this another example here? Or you want to go to the tutorial session?
Maybe, yeah, finish one more and then.
Yeah. Okay, we'll just to go for one of the bending problem here. So can you see the screen now? Example 7.
Yeah.
So this example is about checking a universal beam subject to bending. So here is our beam. It is a simple beam with overhanging cantilever here. And we have the section of this beam is 530 UB 82. So if the section is given, so this means that we are doing a check. So this example is checking. So steel fully restrained along its length, the bending moment is applied about its major axis of the beam under loading. So if this is the cross section of the beam, as you know, how many axes we have for any cross section? How many axes? 2. We have like y axis and x axis. Which one is major axis and which one is minor axis? What do you think? So x-axis here is the major axis, y-axis is the minor axis. Because this is one is major because ix is larger than iy. So if we calculate ix and iy, we will find that ix is larger than iy. Okay? So here it is given that the bending is about major axis. So this means that the moment we have is mx. Because some problems has minor axis, so minor axis means the moment about y. So the factor point loads and distributed load are given respectively. So ignore the self weight of the beam. We need to draw shear force and bending moment diagram. Check the diagram of the universal. Check the moment capacity of the universal beam. So this is the important requirement here after we draw the shear and bending moment. Why we need to calculate bending moment and shear? Because we don't know what is the design moment or what is the applied moment to this beam. So we don't have M star clearly or V star clearly in this example. So that's why it is given the like free body diagram for this example, and then we need to draw shear and bending moment. So if we proceed on this example, what is the first step we need to do for this beam to draw shear and moment? The first step is to find the reactions. How many reactions we have here? 2, YA and YB. To get the reaction, we need to concentrate this load, which will be 80 kilonewton. So if you apply summation moment at A equal to 0, how can we find YB? So YB times 10 minus 200 times 5 minus 80 times 11 should be 0. Do you have any problem with the reactions, or it is easy for you?
That's fine.
Okay, so from here we will get YB. So YB will be 188 kilonewton. If you apply summation y equal to 0, so we have YB up plus YA up minus 200 minus 80, all of that equal to 0. So YA will be 92 kilonewton. So now we have 92 up, 188 up. So how can we draw the shear force and bending moment diagram? So here, for the bending moment diagram, we have, like, if we divide the beam with some sections to help us to draw. So we have section 1, section 2, section 3, 4, 5, 6. So the shear at section 1 is 92 up. From 1 to 2, we don't have any load, so it will be straight. So it is 92 kilonewton. Then from 2 to 3, we have 200 down. So all of this is 200. So we will reach 108. Then from 3 to 4, we don't have any loads, so it will be 108. After that, from 4 to 5, we have 188. So from 18, we go 188, so we will reach 80 kilonewton. Then from 5 to 6, we have 80, but distributed load. So we calculate at 6, it will be 80 minus 80, so it will be 0. This is positive, and this is negative. So this is the shear force diagram. What is the maximum design shear for this one? Or what is the applied shear here? What is the if we want to design this beam, which shear we will use?
108.
Yeah, the maximum, which is 108 kilonewton. Okay, for bending moment diagram, how can we draw the bending moment diagram? Here, if we start at 1, the moment at 1 is 0, because we are at the beginning of the beam. At 2, how much is the moment at 2? Like if we say M2 will be the reaction 92 times the distance 5. So this give us 460 kilonewton meter. Okay, below the datum or above the datum?
If the shear is positive, then you go below for the bending.
Yes, so because it's a shear positive, so this is below the datum. And how we connect them together? Like straight line or a parabola?
Straight line.
Yeah, why straight line? Because we don't have any uniform load. If we don't have uniform load, so we connect with a straight line, right? Okay, what is next? The moment, we can get the moment from the other side as well. So at section 6, what is the moment? 0. Why 0? Because also this is the beginning of the beam from the other side. At 5, what cause moment at 5? It will be 80 times 1. So it will be 80 kilonewton meter. How we connect them together? With a parabolic or a straight line? A parabola because we have uniform load. Okay. Why above the datum, not below the datum? Do you have idea why above the datum, not below the datum? No? Because here, if we look at the shear, here's the shear from left or right? Right. So if you consider the area of shear, it is positive, but because it is from right, so the shear from right is the opposite from left. So that's why it should be above the data. From section 3 to 4, we have no uniform load, so we connect them together with a straight line. So this is positive moment, this is negative moment. So if we said what is the design moment from this example, what is the maximum moment here? 460 kilonewton meter. This is the maximum moment. Okay, now if we go to the capacity tables for the cross section given, these are the values we have. D1 or D is the height, B flange, T flange, T web, ZX, and SX. Z is the section modulus, and SX is the plastic section modulus. Okay, so this is the properties from the table. Now we need to classify the cross section, first step. So the first step is to classify the cross section. So we have flange and web. Same formula we used in columns. So we have lambda E equal to B over T times root F field over 250. So we get now B, which is the width of the flange, B flange minus T web. So B equal to B flange minus T web over 2. So this is the first part. This is the T flange. And here, because it's grade 300, the grade of steel is 300, so F yield equal to 300 MPa. So now we find that E effective flange is 8.27, which is less than E effective plastic equal to 9. So here the section is, the flange is compact. For the web, we will do the same, D web over T web times root F yield over 250. We get this as 57.3, which is less than E effective plastic for web 82. So we have 9 and 82. So this means that the web is compact. So if this in the procedure equation or the design equations, if E lambda E less than lambda E plastic, this means that the web is compact. So what this means? This means that our section is compact. So 530 UB 82 is a compact section. So if it is a compact section, so the section will carry the nominal member, the nominal section capacity. So what we need to find is only the nominal section capacity. Okay, nominal section capacity. So phi in MSX, phi MSX, the nominal section capacity equal to phi 0.9 times F yield times Sx, which give us the maximum moment is, or the nominal section capacity is 558.9 kilonewton meter. So also, because the section is compact, we need to make sure that phi msx is less than 1.5 if yield zx. So the section capacity, the nominal section capacity cannot exceed 1.5 if yield zx. So here, when we check, as you can see, 5.8, 558.9 less than 814. So this means that the section capacity is 558.9. So how much is the applied moment? The applied moment was 460, which is less than phi msx. So this section is safe against bending. Okay, so this means that the section is safe against bending. Okay, do you have any question about this example? Do you have any question? Okay, thank you. So now we will finalize this workshop, and then we go to the tutorial session. Are you okay with that?
I'm all good. I'm gonna have to go, man. I gotta go put my kids to sleep.
Okay, no worries. I will upload the recording after finishing the tutorial. Can you hear me? This what you want, or because your voice was not very clear to me. So you have something to do, right? So okay. Anyway, the recording will be on the